Hello, hey, how's everybody doing? Like that, huh? That's how I used to look. I actually look. This is how I look the same. The other was how I look different. So, but yes, it just I don't know. It seemed appropriate. It seemed like there was auspicious things going on in the world. So I'd go back to my pre whatever it was ways. I don't know. It's getting kind of there's only so much mustache twirling and stuff you can do and be excited about. So, anyway, neither here nor there. Let me start recording. That's always a good idea. I did go through, and with the exception of people who I believe I have reached out to on Discord directly, I have actually graded all of the projects and everything. You know, your grades will be on there momentarily. And good news, everybody looked pretty good. Lots and lots of fun themes there and things. And I think we're showing plenty of creativity, especially with regards to like dropped items and things and kind of the theme of the game and lots of stuff. So excellent. I definitely see that it was funny going through things and looking at code and stuff. After a while, I was kind of like, wow, that looks really, really familiar. I better double check to make sure everyone's not copying off of one another. And then I realized, it looks very similar, of course, to the example code that I wrote. So I can't really say like, well, that's an issue. So looking forward to, obviously now, in case you haven't noticed, in this next project coming up and the final project, there's probably not a lot of like exact code to follow, and that's by design now. So we're taking off the training wheels and we're trying to like do stuff. So hopefully you've had some pretty good examples, and we'll continue to do so, and we'll get there from here. Hopefully, if you do have any questions, I haven't gotten a lot of questions with regards to this project yet from most people. So I'm hoping that it's not a matter of everyone waiting until the last minute. But if you are having questions, reach out. That's what Discord is all for. Don't worry, there's no such thing as bad questions. There's only bad solutions. I mean, something like that. So let's see where we were today. And picking up from where we were last time as well, I wanted to, in case you didn't see my sort of follow-up on Discord, the craziness that was going on with regards to the collision detection and sort of stuff. And it is sort of an age-old sort of issue in Unity, that this problem when you have an object, a game object that you want to cast a ray from that game object to some other game object, and you're using line cast or ray cast or some sort of casting. And the problem is that if you have a collider on that object and you cast a line from that object to some other object, the first collider that it collides with is generally the one that's on that object itself. So it sort of self-occludes. So if you have an enemy that's trying to figure out, okay, can I see the player, and is it occluded by any other enemies? Is anybody else standing in the way? The problem is that those enemies are also on that same enemy layer, and it becomes sort of a problem because if you first see your own collider, then you think, I can only see enemies, and you get this kind of self-occluded situation. And there actually is it's so much of an issue, or it's a known issue, that Unity has in the physics setup and in properties. Now we'll switch back over. Let's switch. You've seen my face enough now. And here we go. This is not the Unity that I want to show you. Let's see. Hopefully Unity is coming up and running. This is all part of my reboot, unfortunately. I don't know what happened. My computer suddenly couldn't see any of its USB audio and video devices, which was kind of scary. A little drink of soda here. It's interesting. Getting used to not having a mustache anymore. It's kind of great. So let's see. Unity's taking a while. Oh, and what are we going to talk about today? I'll start talking about other stuff while Unity is loading. This is sort of an in-between, and we're going to talk about specifically some more stuff on physics, because this project is an opportunity to use physics in sort of some interesting ways in terms of, potentially as you're hurling items, there's projectiles and we're putting forces on those projectiles in order to get them to move. And maybe even, when they hit something, they impart some sort of force on that object that they hit, and so on. So it's a good time to kind of talk a little bit more about physics and also take a closer look at execution. What I mean by execution is like, where does stuff actually run inside of Unity and inside Unity's code, inside the engine? Some people have asked like, well, okay, or maybe it was recently in one of my other classes about thinking like, well, where's the best place or the most optimal place for particular code to run and, simulations to run and so on inside of Unity. And this is a good topic to kind of talk about that in, because we've had most of our code happen either in, can happen in start, or can happen in update, and it happens on collision. Now, those are kind of the three of the main areas that we're kind of hooking into Unity's system, in addition to like writing our own functions and our own methods that are kind of called when, other things call them. So you might be wondering, well, what else is there out there? And it turns out there's a bunch of stuff that's worth knowing about in case you are kind of being careful, or you're trying to be really careful, have some kind of specific desired outcome with regards to how physics behaves and how, one object relates to another and how its call loop happens and that sort of thing. So, okay, first off, Unity's back. And let's jump back over to the scenes, and we had, is it there? Yes. Okay, we have the shoot 'em up going on here, and I wanted to just kind of resurrect this one again. And just because I also started adding the actual bandits down here. If you can see, this is an actual bandit. Someone, once upon a time we wanted bandits in the game, so I had to find some sprite bandits. And we had this mole character that we were sort of using the other day. And let's kind of pick up where the mole left off. And I provided this as sample code. So if you were paying attention in the Discord conversation, there actually is a working version of this this kind of enemy AI code worth checking out if you're interested. So here's our little mole non-player character. And the idea behind the mole at this point is he's pretty simple. And so he has a sprite renderer just to show his image. He's not animated yet. Haven't animated the mole yet. It has a circle collider, and it has a rigid body 2D, which has turned, two things have changed on the rigid body from kind of the default. One is turning off gravity, because I don't want him to fall down. We don't have downward gravity in this game. And I also added linear drag, so that if it gets hit by something or it moves according to physics, it will slow down eventually, right? If you don't have linear drag on things, or angular drag, they will tend to want to kind of move forever. They don't slow down. They don't have, pull on them, right? So if you were doing an asteroids game, you probably wouldn't have linear drag because it would be in space and you want things to spin and float and so on. Or maybe you wanted to just kind of do it. Or in our case here, we wanted to act like, okay, if it's hit with a certain force, it eventually does slow down. It doesn't just keep floating off forever. So those are the two things that I changed in here, and that should probably be on most objects in a game like this, where we don't want them falling downward and we don't want them floating around forever. So we have this linear drag and gravity. All right. I also froze the rotation so that if something bumps into it in kind of an odd way, it won't make it spin around, right? So that's the other thing that I changed. So those three things, right? Okay, it's a dynamic rigid body because I do want it to react to physics. I want it to be simulated potentially, right? Part of the simulation. But there is some behavior here. And now this is interesting because it has a rigid body on it, but it has some scripted behavior. So it'll try to move according to the scripted behavior, but it will also be subject to physics, right? So we're always playing this game between, balancing scripted motion and also potentially having physics interact with it. And this here kind of comes up with a reasonable, happy medium. It's worth considering as an example. All right. So, before I entirely look away from there, the other thing, of course, has a circle collider on it, which is fairly default, just kind of a circle around here. And you'll notice it is what's called mole, and it's on the enemy layer, right? So it's on the enemy layer. Now, in the game, in the scene here, I have the enemy. I also have these obstacles. I have a grid that has obstacles on it. One of the layers in the grid that is a tile map, right? And if I looked at just that one, let's do this. I'll say Window, 2D, Tile Palette, so that I can then kind of focus on, say, the tile map, right? This is the obstacles tile map. And if we look at it, this is really what defines what things can potentially be collided with. Why? Because this layer, this game object, which is a tile map, has a tile map collider on it. And it also has a composite collider just to kind of smooth it out. Right? Because of those two things, things can collide with this layer. Any tile on this layer is collidable. Okay. But I also have a background which does not have a tile map collider on it. And I have this other tile map, which is sort of in the front, which also does not have a tile map collider on it. Right? So I'm using a background, I have a foreground, and then I have these obstacles that things can bump into. Right. So now let's go back to the mole. The mole, and we will then close out it's closing the tile map or the tile palette from my other screen so that I don't wind up. So there's the mole, and he's doing his thing. And we're gonna also, let's see, we're gonna prefabs, and you'll notice I haven't made a mole prefab yet. But now that he's kind of got everything on that I'm kind of interested in, I'm gonna go ahead and make that mole into a prefab. And I'm gonna put a second mole in, or we're gonna put a couple moles in the screen. Let's see, there's a mole. And there's a mole. Okay, so I have 3 moles. And if I press play, let's see, we'll come over here. It won't maximize, but we'll press play. And let's watch what our moles do now. Hopefully everything will behave. All right. Oh, there's lots of other things in the game. So here I am. I'm going to shoot some arrows and try to get rid of those guys. First off, added feature. Yes, there are explosions now. The moles, however, you'll notice the moles don't explode. The moles are invulnerable, I think. I left them being invulnerable. Nope, yes, they are. So the moles are affected by physics, and you'll see that they will, I can push them around, but now they will kind of track where I'm going. Notice how this mole and this mole over here stopped tracking me, right? Now it's they're tracking, and boy, everybody's going crazy over here. Let me some of these guys. All right. So they're tracking. All 3 were tracking. If I duck behind this wall, none of them will be tracking. Everything else will be trying to blow me up. I come over here. Now that one is tracking, but if I hide behind this one who is facing the other way, they can't see me. But then if I wind up there, and so on. So I can sort of hide behind one mole. That guy's like swimming or something like that. I can hide behind one mole so that the other one can't see me. I could get elaborate. I mean, maybe as I get into, having the animations of those moles, they have to be like facing the other way. And then I could hide behind the one and see the other. Or if it's facing my way, then I can't hide, and so on. But for now, the idea is that I can hide behind one enemy from another enemy. It's kind of crazy. So how does that work? All right. What was the difference? What made it work? What did I discover? What made me feel good about all the experiments and trying to break them? What happened was it suddenly dawned on me saying, well, sometimes you have to look at things from an entirely new angle. You have to break something in order to come up with a better way. And that's kind of what happened. I kept saying, okay, well, it's always about, well, the mole wants to find the player. And the problem is that, of course, the mole sees other enemies that's in the way, right? And the problem is that the mole has its own collider and it's an enemy, so we don't want it to see itself. So it got tricky. And then I thought to myself, well, what if instead of looking of, the mole does have to be looking for the line of sight, or at least for the field of view, right? We have to say, okay, is the mole facing in that direction? And this code still has that in mind. It has this, I'll make this a little bit bigger here even. The first thing the mole does is it says, okay, let's create this target vector and let's see, is it in the line of sight, right? Comparing the direction from the mole to the player, comparing that to its look vector, right? The look vector is what I figured out. Okay, it started out, the look vector was just looking down. And it said, okay, so if I pass in front of that, that vector, or along in a similar direction as that vector, this would increase and eventually go greater than 0.6. Okay, I would be noticed, and I use the debug draw line to see where that is. And then here was the bit of the epiphany that I had. I said, okay, well, instead of drawing a line from, or casting a line from the mole to the player, in which case it's going to collide with itself, I said, well, what if I looked at it from the other way around, right? If the mole can see the player, the flip side of that should be the player should be able to see the mole, right? That's the same thing. If there's a clear line from one to the other, there should be the same clear line from in the other direction. And the cool thing about that is then I can say, well, all right, cast the line just in the opposite direction. I swap the from and to points, right? And then I say, all right, I'm interested. Do I hit any obstacles or enemies, right? Do I hit any obstacles or enemies as I look at the mole from the player, right? Now, hopefully, or maybe, I'm going to intersect with one enemy, which is going to be that mole itself. But if I hit any other moles, if I hit any other enemies, any other game objects that are tagged as enemy, I know I can need to make a decision to say, is that the right one, right? So I say here, I said, okay, if hit target equals true, then what I do is I do a simple comparison to see, okay, look at hit target.collider. That's the game, and that's potentially the thing I hit, right? Hit target.collider.game object tells me what game object did I hit when I was drawing that or casting that line. So I can see, okay, is the game object I hit the game object that this component is on, this mole, right? So I see, okay, which object was hit, and is it the one that I am currently on, right? If it's not me, well, then I know, okay, you saw, or the player collided, the player's line cast collided with some other mole first before reaching the mole that is looking at the player, right? So that's how it would say, okay, somebody else is in the way. And it says, okay, if in fact I am the one it hit, then it says, okay, that means there is a clear line, right? The thing it hit was me. There's a clear line between the two of us, in which case it draws a line. It figures out, okay, here's the position, and then figures out, to move towards, right? It says transformed up position vector to move towards, using this object's position to begin with, and moves it towards the player by some small increment. And that's that, right? This potentially opens up some other really cool things as well. And other methods have this opportunity as well. You may, for example, maybe you want to be more sophisticated. You might check in here to see, okay, well, it hit some other target, or it hit some other enemy that wasn't me, right? So you could say, but does that enemy see the player, right? Because if that enemy saw the player and was chasing the player, well, then maybe I should also run in that direction, right? So it gives you an opportunity to make, kind of create some swarm intelligence as well, if you want, because you could say, okay, what I saw was this other enemy. And then you could kind of drop down and in here and say, okay, let me check that other enemy. Did it see it, right? So there's some potential for sophistication, but the main idea is there. So I was very happy with that. So I can say, okay, I didn't even have to use this magic setting that Unity does now provide. Whoops, of course I can't find it because that's not Unity. Come over here, Unity. And Unity has in here, in our project settings, in our Physics 2D settings, you can now say queries start in colliders. And that is used to say whether or not rays or line casts that start inside a collider actually detect the collider that they are within or not. So you can say, okay, you know, if you did want to view it from this character to other characters, uncheck this, right? Whether rays or line casts start inside a collider. If you uncheck that, then it assumes that if you are starting a line cast from inside a collider, don't consider that one collider. So there's a feature for us to deal with that. All right. So let me pop that window out and double check to make sure, is anyone asking questions about this whole thing? Nothing immediately jumped to mind. So any questions on the whole general collision there? Right. Nope. Okay. So the other thing I wanted to mention now as we get into the physics aspect of it, right? And this is a pretty interesting use of things here. Now, the thing you sort of have to be careful in this regard, in that this type of movement that I'm doing here, this vector 2 move towards, where I'm directly modifying this position of this object, it potentially has some issues, right? It is directly manipulating this game object without regard for physics, right? It's just saying move towards, it's changing its position, which is potentially a problem. What's the problem? Well, this object here, this game object, may try to move through other objects that have colliders that it should collide with. And that's potentially a problem. Now, one way around that, and I'll just kind of introduce this concept in here. If this object does have a rigid body on it, which in this case does, I can actually tell the rigid body to do the translating. Why can't I do it from here? There's a way, and I'll as we get into the lecture, there's a way to, rather than manipulate the position of the transform, you can actually ask the rigid body to do the motion for you, which is slightly tricky, but possible. But for now, let's consider this one. And it actually does work reasonably well. No, in this case, you wouldn't want to use a character controller. Well, I mean, a character controller, the normal character controller that you use in Unity is a 3D character controller. There is no 2D character controller, really. So how you sort of have to build your own if you're doing a 2D character controller. Was someone asked, just in case anyone's just watching this on YouTube, the question was, would it be better to use a character controller instead? And ultimately what we're doing here is we're writing our own character controller. So, it depends how much, how much you want to develop your own or how much you want to shortcut it. But ultimately, a character controller is, sort of meant for, usually you're using it with your player character, but you could use it with a non-player as well. And it's sort of, a character controller is and isn't, I mean, normally you use a character controller without a rigid body. So even that is tricky to use with regards to physics as well. It kind of bypasses normal rigid bodies, right? So that doesn't necessarily get you past there, but they're, depending on how you're doing it, you'll come into some of these same issues potentially, depending on your approach to it. So, but let's see, if you notice in the game here, the end result was actually pretty reasonable. So at this point, let's look at like the movement of our moles here, right? So as long as they're tracking me, and let's shoot some of the other things. they are kind of doing the right thing, and they will collide. So, you know, actually the collisions pretty much are happening correctly here. Yeah, so I think we're in that kind of gray area where it works out anyway. So they're moving themselves, reorienting, but they're moving by such a small amount that then the physics engine can kind of enforce what should be going on, right? They have a rigid body on them. They have a collider on them. So everything is happening in combination well enough, and the amount that they can move is small enough that more or less everything works out to our advantage here, right? They are colliding because they can't move that fast. If these things actually moved very, very fast, we might run into issues, right? So a lot of the time you can come up with, reasonable results using these sort of combinations. And ultimately, like was asked, you wind up, generating these sort of hybrid solutions to allow for, it's like they do actually even, it's kind of cool. My arrows, they will impart some force on them. So they will actually get repelled back. Watch this, wind up, bang, right? So the physics engine is working on them, but then my AI is really kind of very, very, very simple, right? The AI is just using a move towards. Now I could make it also that the AI, instead of using move towards, I could say, well, how about you just add a force and really go with physics? Can really go full on simulation if you want. So let's talk about that a little bit. And that's a good segue to get back to the materials, all right? So any questions about, how this sample is working at this point, right? So we've kind of gone through most of the techniques I'm using in here, right? I'm using a simple aim with the mouse according to, the difference, the vector that I'm forming by moving the mouse around the screen versus where the player is, right? And their typical motion is just a WASD-based motion. And then I'm setting up my animations potentially based on, how that motion is happening. Most of the AI is, following the simple dot product and move towards, according to a line cast or a ray cast. So hopefully these things are generally making sense, right? Sure. Not in the area. Are they looking in that direction? Nope. Okay, so there's two things. And you have to say, are they looking in that direction? Right? That's the dot product, right? Because you're gonna have a orientation of the player, and then you have, all right, so here's let me here we go. We'll come up with a good example that's directly in here. All right, so imagine the mole here and this orc here. They're doing something. And all right, I'm going to open up my cool, hopefully my cool pencil thing that I can draw on the screen with. Here we go. Okay, so this guy here, oh, he should have been yellow or something. That's better. Or green, probably. No, anyway, you can get sidetracked. So let's consider this orc down here, right? Now the orc right now, according to the general thing, if he's looking down, that means this is his look vector. He'd be looking in this way, and I'm keeping track of that. Anytime he moves, I figure out, okay, what direction are you moving in? Use that movement to consider that to be your look vector. So he's looking in this direction. So if, say, this was the player up here, we'll call this mole the player, we would say, well, okay, does this orc here see the player? So we would say, okay, let's calculate this vector, which should have been a great line, but obviously wasn't. And that's easy to figure out. It's a straight line is saying, okay, from this position, or we'll subtract this position from this position, that will give us a vector, right? The player position, or the, yes, this in this case, the player's position minus the orc's position gives us this vector, right? So that is the target vector if we're really trying to figure out, you know, is this guy interested in that? Then we have the look at vector, which points in this way. Doesn't matter how long it is. Just imagine, you know, he's just looking infinitely in that direction. Now, the dot product, basically, if we take these two vectors and we normalize them, we set their length to 1. We set that one's length to 1. And we dot product, the dot product will tell us, okay, how much do they overlap by? Do they completely overlap? If they completely overlapped, if this guy was looking, his look vector was in this same direction, the scalar, the dot product, would wind up being equal to 1. If they're in opposite directions, like they are almost here, the dot product, that scalar, would be minus 1. It'll be 0 as it crosses the perpendicular to the vector that we're trying to project onto, right? So it's really just telling us, comparing these two vectors to see how aligned are they? How much in common do they have, right? Two normalized vectors, dot product, we get a 1 if they are completely aligned. We get a -1 if they're completely in opposite directions. We get 0 if they are perpendicular or orthogonal to one another. If they're like this direction, the dot product might be something like 0.7 there. So it's right. He potentially sees him in his peripheral vision there. Now, what is the line cast for then? What's that all about? All right. So line casting, ray casting, they're basically two different things. Well, there's very, very similar things, I should say. One just uses a ray, the other one uses a line. And the idea here is we're also using the same target here. We're saying, okay, here's the NPC, and here's the PC. And we take a ray or a line. If we go from point to point, if we have the 2 points, we might just want to use a line. Okay. We cast that line into the scene. Now, the important thing is, with the line even, we do have a from and a to, right? We have a direction. We have a start and an end. Actually, that's the real terminology is start and end. I don't know why I went from and to. And what it does is it says, okay, it starts the line and it draws the line, and along the way, and in our graphics, if we look, there actually is a wall right here. Okay. And the wall has a collider on it. So as I'm drawing this line, I hit this collider. And that will be, in this case, since I'm using the simplest line cast, which just gives me the first collision. There's ways to find every item along here if you wanted to. That's just more work for the engine to do, right? We could ask it to do that and give us every object it potentially collided with. But I like to be efficient and just give me the first one, right? So the line cast will give me this obstacle. And now I can say, okay, if it was looking somewhere in this field of view, because that's what my dot product told me, but then I cast the line and it says, but I see an obstacle, then I don't see it. Now, I did that. We did our trick to see, all right, just in case this is an enemy and maybe there's another enemy here that I want to have it block that view. That's why I cast the line backwards, right? Because I know that the player is not an enemy, right? That was my trick here to say, okay, I know I can cast this line in this direction and I won't hit an enemy if I'm starting from the player. And if I do hit an enemy, that means, well, there must be a player right on, or an enemy right on top of the player that's blocking the view from this other, kind of guy. Okay. Exactly right. It's using the physics engine to figure that out. Now, so in the case of ray casting, just to cover it, okay. So a line is going to be start here, end here, and give me potentially anything that gets me to that point. In the case of a ray, what I use is I have a ray or a vector, right, which is going to be giving a direction, and then I tell it, so I have a direction and usually a distance. Whoops. Should be just 1, 2, yeah. To say, okay, how far in that direction do you want to look? So if I knew that, the field of view on this character is 6 meters, I could say, give it a normalized direction and give it a distance of 6. And that would say, okay, I can't see anything beyond 6. So I'd be looking at things, just within that radius. So that's a cool thing too. So sometimes you want to use a ray cast, sometimes you want to use a line cast. It depends on what you're trying to accomplish. There's more complex versions of casting where you can even get into the notion of saying, okay, cast a circle along this path. So if you had, you wanted to get real sophisticated and you said, okay, well, maybe this is just a keyhole here and you shouldn't be able to put a cannonball through a keyhole, right? There are things you can do, like take an object and cast it along a line or cast it along a ray instead of just casting, a infinitely thin line. So depending on the engine, you can do some pretty cool things. So casting, in this regard, we're not talking about like kind of the programming version of casting where you cast one type of data to another. We're using casting here to be more like pre-drawing or drawing phantom objects in the scene or phantom elements into the scene to see what do they hit. Right? That's really what it's about, this sort of casting. What does it hit? Whoops, I lost my pen holder here. All right. So we got it? We're good? All right, we're good. Important concept, right? There's also things where you want to say, okay, I want to cast a ray from the camera into the scene in order to pick an object, right? So that's another case where casting comes in. If you needed to say, okay, let me, pick something in the scene, we do that through casting as well, right? It may happen underneath the covers, or there may be even some, shortcutted versions of that for you, but it exists. It is there. It does stuff. All right. All right. Very good. So let's get back to the presentation portion of our program here. So running code on time, a little bit more physics and a closer look at execution. Now, also one thing to this public service announcement, there's getting to be lots and lots of different versions of my lectures in my YouTube channel now. So if you go to my YouTube channel and you search for a particular topic, you may very well find, a couple of different videos, or maybe there's one particular video where a class kind of wanted to go in more depth on something. So if there is a topic that's not, or it's one in the playlist, or you want a different, review of it, feel free to search through my YouTube channel or any other YouTube videos for that matter to kind of get different concepts. But anyway, this one I always remember. Oh, a little extra bit of stuff here on the screen. Let's see. Can I do that? Okay, clear the screen. Running code on time, more physics and a closer look at execution. Okay. Now, first off, let's review the big picture. The current scene is a collection of game objects displayed according to a hierarchy. Game objects themselves are just a name, a tag, a layer, and a transform, right? Without having any sort of components on those game objects, they really are just sort of something that hangs other stuff onto, right? So we have just some basic things to them, and it is a hierarchy, and you can even parent things within that hierarchy. Normally, each game object will contain at least one, but possibly many components, monobehaviors, right? We've seen that. You can even have multiples of the same type. You could have multiple scripts. You could have multiple colliders. You can have multiple rigid bodies, I'm pretty sure, if I recall, if I'm remembering correctly. So there are certain types of components that you can't duplicate, but you generally have at least one, possibly more. Many of those components are provided for you: transforms, box colliders, sprite renderers, cameras, and so on and so on. And other components we write as new C# classes that inherit, which is copying and modifying from monobehavior, right? We are using inheritance already. So this is foreshadowing to some more topics as we get into really thinking object-oriented and inheriting, right? In our scripts, they all began generally as monobehaviors. We did a little bit, kind of hinted a little bit some of the scriptable objects and things, and sometimes you even have classes that don't inherit from monobehaviors, but if you want to make components, they inherit from monobehaviors. So when you click the play button, for example, Unity automatically iterates over every game object in the hierarchy, everything in your scene, iterating over every component in each game object. So what do I mean by that? Like, remember when we wrote a component here, right? We had this start. Okay. So you might have wondered, where does that start happen? And since start was built into MonoBehavior, stands to reason that there's a lot of those out there. There's a lot of start methods. There's a lot of update methods, and they get called a whole bunch. So the question is, where does that happen, right? So we click the play button. Unity somehow automatically iterates over all of the game objects in your scene, everything in the scene, iterates over every component in each game object to start them all. So it's a 4 within a 4 potentially here, right? We're saying for every game object and then for every component on that game object. And then it invokes various routines. So by invoke, I mean here, execute. It runs, it does, it runs that method, it runs that routine. The start function, the start method of that component, if it has one, right? It may not have one. We may have deleted it, but we may have one. So that's happening once when you hit the play button. Boom. Sooner or later, it calls the start of every component and every component of every object in your scene. And then thereafter, on every frame drawn to the screen, however, whatever rate that might be at, Unity will again iterate over every game object, iterating over every one of its component in that game object by invoking the update function of that component if it has one. And then finally, after it's done all that, then it actually displays the frame, and voila, it repeats the process. So over and over again. So that is your main game loop then, kind of running that piece of it. And that's sort of a big while loop until the play button or exit condition happens, right? So that's the two sort of big loops that we have. There's a for loop here with sort of the play, where it just runs through until it has started every component in the scene. And then thereafter, it's constantly calling the update routine over and over and over again until gameplay ends, or at least until that scene is unloaded, potentially. Right. Whew. So, stands to reason, or maybe it begs the question, or maybe you didn't even care, but what other functions are there potentially, and what might their use be? So one of the other ones that we like to talk about first off, because it is first, is this thing called awake. So awake happens even before an object starts, right? It happens when an object is initialized. So we have awake, and then we have start. How do we add an awake routine? Well, we can actually go ahead, if we wanted, we could just say void awake. Now we have an awake function. This awake function will happen before start happens. Seems weird. Why would you care? Why would you use awake instead of start? Why do you have both of them? Well, there's some good reasons. It is useful for initializing objects that other objects' start functions need. What does that mean? Well, there's a question. Oops, maybe a question. Sorry. So the basic idea is, imagine that in your code, you wanted to say, okay, let me check. In start, the first thing I want to do is check who else is on the screen, right? Or what other enemies are in the scene, that sort of thing, right? And you can't be sure of certain things. You can't know whether or not their start routines have been called yet, right? So if you have this kind of weird situation where what goes on in your start routine potentially, weird question, but if you have a set active on false for an awake for a game object, then have the game object on awake. Which will happen first? Awake, set active on false. Wait, if it's inactive, you wouldn't start. I believe awake does happen even if set active is false, so that you can potentially wake up later. Awake won't happen when you activate, right? Start happens when you activate, but awake happens just once for the game object. I think we'll show that, but that is a good question, very good question. All right, so this is the notion. It's like, okay, there's stuff to happen, but potentially there's lots of stuff that everybody needs to coordinate on, right? So say you have a whole bunch of things and you don't know, like even if you have a whole bunch of static objects that are all like looking to do something, it would maybe make sense to have it in the awake routine because you don't necessarily know. So it's potentially a way even here to kind of clean up some of your singleton functions if you're using start for that instead of using awake. But anyway, so we have awake to help deal with that. So if you know you want to have something happen first before anybody else has a chance, you want to set up something so that everybody else knows about it within their start, you put it in somebody's awake function. Yep, there we go. I'd forgotten. I give this lecture in a while. This does run even when a component is disabled. Okay, so disabled means active is set to false. So you have to deactivate the entire game object to prevent it from running, right? This is the component, all right? This is also like, so if you want to prevent awake, you deactivate the entire game object. But this is why I wasn't entirely sure when you're saying set active here. If you deactivate the whole game object, then the component won't be active or won't be awakened. But if that component is disabled and the game object it's on is activated, it will be awakened, but not started. I forget. Too many game objects. We just started Unreal game engine in Game Dev 1. So I can switch modes back again. All right. So awake, that's supposed to be the thing that happens first. All right. So you might remember we had update. And of course, what happens if you want to have something that happens after everybody has been updated, right? If you want to have something happen before everyone's updated, you do it in start. But what if you want to have something happen after everyone has updated? You potentially put it in late update, right? So this is a convenient way to have an update function, or if you want to have something run during update, but run after update, it runs in that same loop, but after all the other ones, right? So everybody has drawn on the screen potentially, or tried to draw. And then if you knew that I want to have something that does something to every rendered object in the scene or every modified object in the scene, you could call it in late update, right? If you know you're trying to affect lots and lots of things, right? You would check for collisions, or, well, not really, but it runs after all of the update functions have been run in the frame and after all the animations have been computed, right? So if you want to do something that is specific, that is affected potentially by all the movement and animation and other calculations of the scene, you can put that in late update. So guarantee, you use this when you want to guarantee that it happens after all the updates, right? Because update order is arbitrarily set on play. Each one of these, right? Everything that's in update, you can't really tell which game object, which component, which update happens first for, all of them that are out there. Whoops. You don't know whose start routine is going to get called first. You don't know, even it might look that way in the hierarchy. You might be looking in this tree here and hoping that it happens in this order, but not necessarily, right? The order that starts and updates happen, no guarantees. That's why Unity provides this awake and start, update, then late update. Yes, and it's after, and you have to think of it this way: it's awake is before anybody starts. right? Not just you. And late update happens after everybody calls update, right? So every component has already done its update. Then late update happens, right? Everybody's awake call happens before start. Anybody's start happens. But you can't guarantee that one awake happens before another awake. So, there's only so many, as they say, it's turtles all the way down. At some point, you have to say, well, all right, they give you enough layers to hopefully deal with things. So that's why we, don't have infinite layers in here potentially. But all right, so here's what it looks like. Right, here's your loop, and inside of any of these, there's actually some additional loops, because this isn't just this component. It's actually all the components that are running in the system, right? So you have the awake happens, start happens, right? Every awake happens, I should say. Every start happens. Then we get into this loop where every update is called, then every late update is called, and then we loop back and we call every update again, and every late update again, and so on and so on and so on, right? Whew, that's a lot of stuff. So certain mono behavior functions, let's review. Start, called when mono behavior is activated or started. Update once per frame. We also, you may have seen, on mouse down, right? So anytime the mouse is pressed, everybody who has registered we're getting there. Don't be stealing stuff from my presentation. It's like even newer version. Okay. All right. That one's, anyway, that's there are, this will help. Don't worry. And there's some great references out there. So I want to talk about the specific, issues and why you might want to do this. Okay. So we have on mouse down, and I don't know if did that have everyone in it? Probably didn't have everyone in it. Anyway. All right. So for example, then we have on collision enter 2D, which will happen. All the collisions will happen, right? And so on. So generally, we're looking at this notion of awake start. Then we have our input routines happening first, then update, then late update, right? Yes. Absolutely. Yeah. Remember that in code organization is like that. The order that you put something in your actual file does not matter unless it is within the same method or function, the same block, right? The class itself, the order that certain functions are in a class do not matter with regards to the timing of execution. It does not, linearly go through your code there, right? Hopefully that made sense. Right. If this method here, awake and start, I could just as easily put, awake, down here, as long as it's in the class. It's the name that determines when something happens, not the position here. Of course, code, once it's in update, it's going to progress generally linearly through here, unless you do something crazy like put in, go-to kind of, things, but, it's fairly arbitrary, certainly, because then you can have, subroutines and things that call back and forth and so on and so on. You want to be kind of careful. Sometimes you want to be careful how to do that, because maybe the compiler, certain languages in general, might get upset one way or another about predefining and post-defines and things like that. But anyway, that's a whole other. So, okay, now this is where it gets fun. So the physics step is calculated in its own loop, independent of the master loop. And I'm going to do a little bit of hand waving here, not necessarily explain how Unity handles multitasking or multi-threading. That's a concept that's kind of open to things and newer versions. And now there's the entity component system and ECS and dots and all that kind of stuff. Things kind of potentially change here, but for practical purposes, for purposes of design and where we're at right now, we're going to consider the physics as being calculated in its own loop, independent. So it's happening, imagine, for all practical purposes, it's almost like it's on another process, or it's on another thread inside your computer, right? It's happening basically, and you notice in quotes here, simultaneously, according to the other code, right? So you have update happening, and then you have this other physics update happening independently of that. Now, why is that? Okay. That all comes down to kind of rate and speed and timing and physics, right? In the case of physics, a lot of the time, and this goes back to our, this is kind of probably reinforce some of the why we use time.delta time in a lot of cases, right? And remember, we talked a little bit about jerk and snap, crackle, pop, and we had acceleration and jerk and all these sort of wonderful physics concepts that are all governed by what interval of time, what is what is changing over the course of time. Speed over time, right? Speed is distance over time, miles per hour, right? So how much distance is changing in a given amount of time? So we like to sometimes refer to that as some sort of immediate thing. We say, okay, I'm moving at 65 miles per hour right now, right? You look down at your speedometer and it says 65 miles per hour. You know instantly kind of what your speed is, but you're not saying I just traveled 65 miles by looking at that, at any particular point. That's not what it's telling you. But it's saying, okay, over some given, if you continued at that speed over an hour, you would move those 65 miles. But the amount that you actually move depends on, how much time you're willing to move at that rate. Okay. So distance, the actual distance that you're moving, is basically an accumulation of speed over time. How long, over what interval or intervals do you travel at that speed? That gets you your distance. And the sum of all of that, scaled up by corresponding time slices, right? That's why we have these time slices here. It will add up to the total change in distance. Whew. So it's almost like calculus there, right? We're integrating, we're adding, we're summing, we're taking not infinitely small, certainly not infinitely small with regards to the engine in our game, because we have some slice of time that we're working across to figure out how far we've moved or how much we've sped up and so on, right? That's why we have to have some reliable way of determining the passage of time. It can't be just arbitrary. Like, how many frames can you draw per second? If that changes, well, we can't have the physics in the world changing, right? Now, anyone recognize this equation? I hope. I certainly hope. You've all probably taken some physics in one way or another. Good old force equals mass times acceleration. Let's come up with some really cool or some kind of arbitrary Fred equals, no, force mass times acceleration, sort of in our case, right? We're in a simulated world, and we're not in the real world. So we're going to say sort of. And I apologize for this. I scaled these wrong. Okay, apologize. Acceleration is the change in velocity over the change of time, right? Acceleration is the change in velocity over the change of time. A equals dv over dt. Delta velocity over delta time, right? Velocity is the change of distance over time, delta x over delta t, right? So if we think about it, this is basically acceleration is the second derivative of position over time. Right? And now, yep, I warned you. So basically what we're doing is we're trying to accumulate the change in position according to the change in velocity over time. So we can figure out, right, given some amount of time, we can even do things like say, okay, say we want to figure out our speed. To figure out our current speed, what we do is we say acceleration times time, right? How much acceleration has occurred plus the last velocity we were at, right? So just like if we want to move our distance, want to move a certain distance, we have to say, okay, over the course of time, how much have we changed? We may also need to figure out, okay, what is our current speed? Well, that depends on how we accelerated over the course of time, right? You floor the accelerator in the car, you're going to accelerate much faster. So you're going to reach a higher speed in a shorter amount of time if you're accelerating a lot. If you're accelerating very slowly, it's going to take you longer time to increase your speed, right? So that's why this acceleration term here is so important. And then we can say, well, okay, if we accumulate that, then we can say, how far do we travel according to the accumulation of our velocity as it is increasing according to acceleration over the course of time. Whew. All right. So now we're getting there. We have a formula. We have an approximation basically here that we're going to use to figure out our distance. Now, in the ideal world, this is what would happen, right? In the real world, we kind of think this way. We have some velocity, we have time, we are smoothly accelerating over the course of time, right? But the problem is, in the digital world, in the computer, we don't have infinitely small slices of time. We execute things at discrete times, right? Computers are discrete. They work in steps. They have some sort of time interval that they work on. So we can figure out, we can calculate what that velocity should be according to time as we accelerate, how much time we spent. We can calculate that, but at any one of these particular steps, depending on what granularity, depending on how fast our loop runs, that's going to say, well, how closely do we really fit this line? How good of an approximation are we here? Maybe this looks fine. Maybe, we hit that line at this point here and here and here. But if we average these values, our line wouldn't really hit there. Our line would hit somewhere in between, for example. So there'd be some sort of error, right? What we really wanted to do is come up with this, but we missed all these gaps potentially, right? Imagine this even, if we're not even smoothly accelerating and we're, deciding to accelerate and then slow down, accelerate, slow down, and so on and so on, then we wind up with another problem because we are potentially slowing down, in which case we start to lose area under the curve. In some cases, we're going to gain area under the curve, or over the curve, I should say, right? So it's all potentially this issue of accumulation of error, right? This is why we need something we can sort of rely on at least to get this, right? So imagine word problem. Here we go, word problems. A car at rest accelerates for 10 meters per second squared, right? Where will it be after 10 seconds? Analytically, we would just say, okay, let's just calculate this out. Let's pop this formula in. Boom, done, right? 500, done. But the problem is that only works at the end of that interval. And we're simulating something. So we can't just rely on the results at the end of that interval. We need to calculate it along the way, right? We need to move it. We need to animate it. So at time 0, we have position 0, we have velocity 0. Then we'll go in and let's start, calculating as we move along. We say, okay, we moved after 1 second, our velocity hit 10. After 2 seconds, our velocity hit 20, but during that previous second, we moved by 10. All right, well, the next second comes along. Now we've added 20 to our position, but our velocity now hit 30. We continue to accelerate. After 4 seconds, our position has become 60, our velocity is 40, and so on and so on and so on. And by the time we get done, because of the error that occurs, we've only moved 450 meters instead of the 500, even though we hit that velocity, right? So this is the problem we're dealing with, right? And it gets worse. It gets worse in that, imagine we have uneven steps of time, which is the problem with games and graphics and so on, is that we don't know necessarily will things execute within the allotted time. Will they happen quickly enough? Will they always happen at a 60th of a second? We can shoot for that, but we don't necessarily know. So we try to smooth that out. We try to alleviate some of those issues by having this fixed update. So fixed update is occurring regardless of the frame rate of the game, right? Unity has multiple update functions which fall into two categories: the main loop and the physics loop, right? So the update functions happening in the main loop and the update functions that happen in the physics loop. Fixed update is happening in the physics loop. They aren't technically running simultaneously. They are running interleaved, and they are interleaved potentially unevenly, right? So it's a little bit strange, but trust me on that one. Update runs in the main loop, and it runs once per frame, however often that may be. Fixed update runs in the physics loop and runs as regularly as possible, which is generally pretty good, okay, regardless of frame rate. And you set this, right? This is actually set. So imagine you have something you want to have run on regular intervals. It's important because you're calculating some kind of position and so on. You do that in fixed update. If you're doing something like user input or setting a velocity or setting some value, that isn't smoothly, doesn't really need to be changed smoothly, you can go ahead and do that in update. Now, I forget if I do this in this, so I'm just going to cheat and show you where this is. So if we go and we look inside of Unity and we go to project settings, inside in physics, is it physics 2D as well? No, go to time. Sorry, I forgot. If we go to time in project settings, you'll see that there is a fixed time step. This is the rate at which the physics calculations and fixed update events are performed. So by default, it's 50 frames or 50 times per second. I shouldn't say frames, that's the wrong thing. 50 times per second. Excuse me. A few other things generally we'll not have to worry about. Frame rate independent interval that caps the worst case scenario when the frame rate is low, right? So if something takes too much time, it will break out of certain routines, right? To kind of try to keep your game running at some reasonable rate. It won't let a frame take more than 1/10 of a second, for example. It'll start not calling update functions. And then timescale allows you to do things like slow down the rate at which physics is occurring, right? So you can do things like create bullet time effects, slow things down, pause the physics engine, and so on. And this has to do with how particle systems run. So you don't have to worry about those too much. Or I know, don't worry about them. Concern yourself with them, but don't worry. Nothing to worry about. Okay, so now we have two loops that are really going on. You'll notice that there actually are on collision and on trigger. Those are actually part of the physics system, and they've been occurring in this other loop the whole time, right? So now we have on mouse update animation, late update and actual rendering of the frame. And over here we have our fixed update, then physics that the engine does, then it calls on collision and on trigger. Whew. There you are, as just a reminder where it used to be. Now we can go directly to project settings. This is the old version. Oh man, gotta update that one. Bottom line. So you should be considering this. There are ways to program around it. The more you see that you're relying on time.delta time, maybe you should consider that is code that should be occurring in fixed update, right? Depending on how you are manipulating things in rigid body 2D, generally code that manipulates rigid body 2D should be handled in fixed update. But if depending on how you're doing things, you can, if you're adding a force that gets added just once as a result of, user input, that can happen. Forces and so on that happen as part of the collisions, Good news, guess what? They're already in the physics loop, right? Sometimes to do this does call for sometimes separating things like user input from the physics movement. So we call that decoupling. So you might find, like if you're doing a real physics-based kind of character controller or input system, you might say, okay, let me grab the input, put it in a buffer, so it's being updated as often as possible, but then only use that value to calculate some new speed or movement or something like that inside the physics update. Fixed update. Right. So, for example, instead of immediately applying a force or setting a velocity when we detect an input, you might set a flag, assign a bool to true, and then in fixed update, go ahead and say, yeah, something changed. Do something based on that. Make that fade away here. If that bool is true, then go ahead and apply the force and reset the flag so it can happen again. All right. So I think we talked a little bit about this one. I don't know. Now, my brain is fried again with all this crazy stuff and COVID and elections and all this kind of stuff going on. How much have we kind of really talked about coroutines? A little bit. Did I mention that? Could probably use a review anyway, right? Even if I did. Who remembers coroutines? I know some of you have used coroutines, and that threw me off in your examples. But let's assume now this thing about coroutines. What coroutines are, so we'll give a formal definition just in case. Maybe give an informal definition before. And the idea with coroutines, they are the big brother of invoke, right? Invoke and invoke repeating, but they're far more controllable. They're far more interesting because we can kind of return to the main system. We can kind of do things at a rate. We can do our fade in. Yeah, I think I showed. Did I? Yeah, I must have. I don't know. This one lecture is kind of crazy because it summarizes so many other things. So it's a good case of using coroutines, using these kind of routines that can be interrupted as they're executed, right? Coroutines are sort of like additional threads or additional tasks that can happen while something else is happening. Sort of like invoke and invoke repeating, but like I said, far more fine-tuned. So in this case, you remember when we were trying to interpolate and we were trying to figure out, okay, move from this position to that position, we had this problem in the other example lecture where we said, okay, we want to move from here to there over some course of time and smoothly interpolate. But if we're here in update, if we're trying to interpolate a position inside of update, we have this problem that if you have a while loop, it's going to sit here as sort of a dead loop and just kind of iterate over and over and over itself until it gets done and then fall through, right? It doesn't really give itself a chance to do this stuff because you shouldn't have these sort of dead loops, or not dead, but kind of tight loops, unbreakable loops inside of a update routine if you can avoid it, right? It's okay if you need to iterate through a certain number of objects, a reasonable number of objects and things, iterate through things for purposes of anything other than time related. You should never wait for time to pass in a while loop inside of an update, right? You really should never be waiting for time to pass without letting the system have some time to pass. That's kind of what the point here is, right? So here's the error in that here, no time can actually pass in here generally. I mean, some time, I guess, could theoretically, if multiprocessing is working in the newer version of Unity, that it used to have real problems with this sort of thing, where if you're actually using multiprocessing and it can interrupt this or run on another task, we may actually see time passing, but assume this is a bad idea. So we have coroutines for that. Coroutines are these special functions that, wow, my cat just said huge. What is your problem? You should all meet my cat because she wants to be let out. Can you all, can we pause for a moment while she's like yelling at me? Okay, wow. I need a breath anyway. So back in 1 second. Callie, what was that? So rude. She's generally super sweet, but she can, when she wants to let me know what's going on, she has no qualms about yowling really loudly. Okay. So coroutines are these special functions that are designed in order for you to execute things at either intervals or according to other things that are happening without kind of tying up execution, right? So you can iterate over things, wait for certain things to happen, kind of create timing-based or smoothly running things without kind of sitting in a hard loop. They may look like they're in a loop, but they're in a loop, but they're not in an uninterruptible state, right? These are functions that can basically exit prematurely, right? We've seen before with an early return. Like if you had a for loop, you could say return in the middle of a for loop and it'll just exit the loop. Or a while and just return or exit or something like that. It would just like exit out. But the cool thing about coroutines is you say, okay, exit, but come back to me at some point in the future. Right? So you can kind of stop or give up control, say, okay, let some time pass, but resume exactly where we left off. And then you get called again, which happens automatically. This is great. This is super useful for kicking off a process that needs to be run over the course of some amount of time and then letting it sort of run on its own. Like if you need a character to fade in or to, move, to interpolate its motion in reaction to something, right? It needs to swing in a certain way. You're not using physics to do it. You just want to kind of create your own sort of animation or sequence of things that happen over the course of time. Right. I just use this for fading in and out, or even having some sort of timed value that can be interrupted. Right. You do that sort of thing. Right. They also have this great ability to wait for other operations to complete. So you could say, okay, do this until something happens, or do this as long as something happens. Sort of idea. So this is that same function as a coroutine now. Right. So imagine here, we've said, okay, we want to move this object. So we're going to kind of set up its own routine here. We're going to move this object starting at a certain position to a certain position. So we're going to move X, for example, right? We're going to move from negative 5.42 from here to here to 5 over the course of time, over the course of 2 seconds, right? So we have a starting time. We're going to run for 2 seconds. How do we do that now? Now it's okay to have this while routine because we're going to say while the amount of time elapsed is less than the amount of time we're supposed to take. We can, figure out the elapsed time over the interpolation time to figure out what ratio, what fraction of time has happened. Do our stuff. And then here's the magic. Yield return null. If you say yield return null within a coroutine, and it's important that coroutines, when you declare a coroutine, it is an I enumerator that tells it to wrap it in the appropriate dressings in order to be able to return and execute. It says, okay, yield return null. So it means go away, but then come back as soon as you can, or after giving the system a chance to run. All right, so you can interrupt this loop at this moment, and next time it'll come back again. So this will run basically still as fast as possible. And even then, maybe now you might want to do something so that it's not always just running as fast as possible. Maybe you want to have this run maybe as an interval. All right. So here's our special dressing, our special sauce here, I enumerator and our yield return null. And when you want to start it, when you want to invoke this routine, you don't just say move, you say start coroutine move. Right? That's invoking it. And it starts immediately running at that point and will continue running until it completes. Right? Eventually, it will have interpolated the movement from that to that over the course of 2 seconds, and then it will just quit, run, be done. All right. So there's a bunch of different ways you can actually yield. One of them being yield return null. That means, okay, stop running and come back to me after the next update, right? So update the screen, update the frame. Go ahead, render one frame. Come back to me when you're done. You can say yield break, in which case, okay, this coroutine just ends there. Doesn't ever come back. There is no return case for that one. You can say, and this is one that I personally love to use because it allows me to say, okay, go off, run for a certain amount of time, and come back to me after some time has completed, right? So if I want to update this at a certain rate, I want to animate this at a certain rate, you can say yield return new, wait 4 seconds and give it a certain amount of time, 0.5. If you said, okay, I want to update it at 20 frames per second, I would say 0.05 for wait for 0.05, a 20th of a second before coming back to me, right? You can also yield return new, wait for end of frame. That will execute the whole frame, but it will call back only after all the rendering and the GUI is complete. So it's a little bit more elaborate than yield return null. It's a little bit more specific. You can wait for until after the next physics step. You can also wait until new routine will run to completion before the yielder is resumed. So this new routine, you'll say, okay, run this new coroutine. And then when that new coroutine is finished, come back to me. Whew. So because we have new routines that can happen all over the place, we have to look at our frame again, look at things differently, right? So now we had our physics, we had our frame update. So we have on mouse X, we have update. Normally, here's where coroutines start and where yield null and wait for seconds comes back. Or you can have your code return within that same update if you said wait for end of frame, right? So you could start something, then let all the animation, the late update, the rendering occur, and then pick back up after that has happened. You can also do things like start things up and wait until the end of a fixed update. Kind of crazy. Lots of control, lots of different options. For the most part, 99% of the things you're going to need to do with regards to this class, certainly, we're not going to get very fancy. But if you just know specifically about how to do updates, how to do coroutines so that you can, have kind of, especially when you're talking about interpolated things or sort of your own procedurally animated things, use coroutines for that. And then know that you have the option of using fixed update, or in some cases, you're urged to use fixed update for certain types of manipulating physics. So that's what you need to know. Whether or not you wind up using awake or late update or, a lot of things, it's all going to depend on the design of your game, right? These are at your disposal, ready for you to do stuff. Whew, that was a whole lot of talking, a whole lot of good stuff. A lot of good background stuff. The main takeaway, of course, is, like I said, the use of fixed update and the use of coroutines. All right. Any questions? Is anyone still awake? Okay, that's good. So let's jump back to my sample game again for a moment. Now, in here, if I recall, there is this one thing. There's this gem over here, which is my invulnerability gem, right? My bonus. And you'll see what happens here if I press play. And I guess maximize and play isn't set. I should have set to that. Let's do this. Let's get it full screen here. Does anyone else out there battle with attention deficit syndrome? I know I do. And this always leads to fun things. Now, so I've grabbed that, and you'll notice now everyone is sort of invulnerable. They don't see me, and I want to have the ghost running around because it's more interesting when the ghost is running around. So I'm not going to fire any arrows. All right. Oh, Now I'm sort of invisible. You'll notice that suddenly all the ectoplasm bounces out of the way when I'm invulnerable there. But now they all hit me and I lost all my life. Here, suddenly, everybody bounces off me and runs away when I touch that. But you'll see that kind of fade action, right? Just so I know I'm invulnerable until I fade all the way back in again. So how does that accomplished? Well, let's go into the player script, and then we'll kind of finish up for the day. So we had our hero. Here's our hero. Hero has hero controller. Hero has his bullet stuff, and hero has a couple of things it can bump into, right? So if it touches a trigger, it will consider, it'll say, okay, triggers in my game I'm using for my power-ups, my dropped items, right? So I have 3 potential dropped items, one being a gem, if it's named gem, the other one being named heart, and the last one being named coin. And so I'm doing a couple of different things here. One, for heart, I just do this instant thing. I just, okay, go ahead and add some life back. And I'm just doing it graphically right now. So I don't have a real life counter. I'm just using the fill amount of my image component that lives on my canvas there. It's called life, right? My coin, I have a triple shot that lasts for 10 seconds. So what do I do? As I say, okay, if I have collided with the trigger, that is my coin, I set triple shot to true. And I also say invoke single shot 10. So let's see. So in 10 seconds from now, I will call single shot. And what single shot does is it just sets triple shot back to false. Okay. So what is triple shot doing? Well, triple shot is doing my triple shot, after all, which is happening here in my fire routine inside of update. So update is basically I hold down the fire button, which shows my little arrow indicator, starts it moving backward. So I press the button. Let's see, I press the button, I set my indicator to active, and I set my starting time. Then this could be an else if I wanted. In this case, I'm using else not really because it matters, but because it creates this relationship. It's more for me than for the execution. It'll execute obviously it worked just fine. But these 3 things should be mutually exclusive anyway. So I'll just do that. So it says, okay, if I press the button, it does this. If I'm holding the button, it basically is saying, okay, handle the aiming as long as you're holding the button, and the pull back, right? I'm pulling things back. Time is elapsing. I'm changing the local position of that game object that shows my arrow kind of being drawn back. And then the third phase here is to say, okay, when I let go of the button, input get button up, fire, that means go ahead and fire the shot. In which case I hide my indicator. I look at how much time has elapsed, how much time I held, pulled the arrow back. Then I say, fire that arrow in the direction that the mouse was pointing. And here's where triple shot finally comes in. So you'll see here to say, all right, if triple shot is not true, so I have this loop here that's going to say, okay, normally, if I just ran this without this triple shot bit here, it would be a triple shot. It would say, okay, for int I from -1 to 2 increments, it's going to run this loop 3 times, starting at -1, then 0, then 1. Why do I do that? You'll notice I didn't go from in the typical for loop 0 to 3. I did it from -1 to 1, which is useful in my case because I want to point 1 arrow to the left, 1 arrow straight ahead, and 1 arrow to the right. Right? So that I accomplish that by saying, okay, instantiate an arrow and then set its direction by rotating it. And the first one, I, is -1. So I rotate it -15 degrees. So it's to the left. I add a force to it and I shoot it. I tell it, okay, die in two seconds. And then I say, okay, if I'm not triple shooting, I would break out of here. I would just stop executing this loop. Right? So the other case is that, okay, this not triple shot, I bypass this -1 and set it to 0. So this triple shot piece here means first time through the loop, set it to 0, even though normally if triple shot wasn't true, I would have this to be -1. So I would do it, I would start at 0 and then end immediately here if triple shot was true. If triple shot's not true, no, sorry, other way around. Reverse that. If triple shot is false, I bypass all this. If triple shot is true, then I don't do this. I use the -1, which means shoot 1 to the left, go to the next one, it becomes 0 here in my 4, shoot 1 at 0 degrees offset, and then shoot the next one at 15 degrees offset. So I'm 3 times through, and I iterate, and I offset it that way. So that's triple shot. Whew. So what's going on inside this invoke, inside of this invoked routine is very, very, very simple and trivial, right? It really doesn't do anything. So I can just turn that off after 10 seconds, right? I just have this 10-second kind of cooldown, sort of a cooldown or run out on my triple shot. So I don't really have anything smoothly, the moral of the story, I don't have anything smoothly happening there, so I can just go ahead and use invoke if I want. In the case of my other one, my invulnerability, not only do I want my invulnerability to last a certain amount of time, but I want to have some sort of visual indication. I want to animate what happens. Right? So that's why I use a coroutine for this one. So in here, when I pick up the gem or I bump into the gem, I set my repulsion ray. That's really what this thing is, sort of my repulsion item here, to true. And the important part that we're talking about now is that I stop any coroutines that are running, which might be, if I bumped into my gem twice, I don't want it to act really weird. So I basically, just in case I bump into the gem twice, first I stop the coroutines that are running, and then I start the coroutine. This is called flasher. Now you can do it one of two ways. You can either say start coroutine flasher like this, or I could have said start coroutine like that. The trivia, you do it either way. This is probably better because then at least the compiler will check that it really exists. If you just go ahead and put something, kind of blah, 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 it'll let you do that. And it doesn't check it, and that will just be bad. So probably better off to do it this way. So what Flasher does is it basically has a loop in here. It's set up IEnumerator Flasher, sets the gets the color of the component that's going to flash, and I could use this on just about anything, I guess, anything that has a sprite renderer on it. And then it goes into this for loop, and this will run from 0 to 2 at an increment of 0.05. Right. So run a bunch of times, and along the way, it's going to increment the alpha from 0 all the way up to 1. So it's going to fade the alpha, the transparency, back up and set it. And it will use this wait for seconds. It'll wait 1/10 of a second in between each one. So if I wanted it to last longer, I could say, oh, wait 2/10 of a second. And now if I come over here and I hit play, I should have a little buzz to make sure you're all paying attention. I don't know. Remote learning, it's such a fun thing, isn't it? Okay. So I'm going to run up here. I'm going to grab this guy, and now you'll see it'll take twice as long It's still pretty smooth. The other giveaway is like, if I'm in that mode, I also shoot really, really fast. You like the explosions? I like the explosions too. Oh, it wore off. Other cool thing, you'll notice these guys here, if I shoot lots of arrows, they're not blinded by arrows, which is annoying. But the other guys, they are actually blinded by arrows. They can't see me through a smoke screen of arrows. How cool is that? Because they're using a slightly different version of the routine that they can be blocked. I think they can. You can have all sorts of fun in your enemy AI. Maybe I not change that. Maybe I change it back. And moles. What we like to do is boom. I have to turn their rotator off. So I've got a bunch of different types of enemies. These guys, hint, the spiders don't do anything. They're just there to obscure your vision. Moles, they're invulnerable. They're to be a pain in the butt. And the orcs are just expendable. They actually explode when you shoot them. Life back. All right. And that guy doesn't do anything yet. If there are no questions, hopefully this has been inspirational. Have a great weekend. Keep making progress on your projects. And I'll see you next week. Have a great one. All right. Take care.